Hey everyone, this is Dr. Calkins again. So we're going to get a little further into week 3, chapter 4. So the next thing I want to cover is understanding where electrons really are. So one of the first things we're going to show you is an analogy. If you take the Earth and turn it into a map, what needs to happen? Well, you have this spherical object that needs to be flat so that you can put it on paper. So if that were to happen, we would basically cut the backside of the Earth, pull this side out, and as we start to unravel that globe, we get some distortion like you see in Greenland and so forth as it peels apart. But eventually we flatten it out, and even with distortion we get a map. So if this is our Earth and we can flatten it into a map, why shouldn't we be able to do that with an atom that has a proton in the middle and all these electrons out here in these little rings? So if we were to cut all the way down to the nucleus, peel this side back and peel this side back, we get a map. And because the space right next to the nucleus is so small, when we flatten it out, we get the shape of the periodic table. So as we were to pinch these two edges together, we would go back to the sphere and back to the atom. That's kind of where hydrogen and helium sit. The reason they sit there is because in this space that only holds 2 electrons, so close to the nucleus, we only have 2 atoms, so we only place 2 boxes in the periodic table. So as we splice this into more and more and more rows, what we're really just showing is this is equivalent to an atom that has lots of rows of seats. So our nucleus in the middle, very few, bigger, 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 bigger. And mathematically we can predict how many fit. Turns out the idea of 2n squared can tell us that. 2n squared says, and n being these energy levels. For us that can be just the period on the periodic table. We would expect 2 times n squared would be 2 times 1 squared for our first period. 1 squared is 1, times 2 is 2. That's basically 2 electrons that can fit in the first period. So if 2 electrons fit in the first period, then how many can fit in the second? Well, that would be 2 times 2 squared, which would be 2 times 2 is 4, times 2 is 8, and if you look at the periodic table, sure enough, that second row does have 8 electrons. So what we're seeing is if these corners were pinched together, we would just wrap this into a globe, just like the Earth, but now an atom. So 2 electrons fit in the first period, 8 electrons fit in the second period. But then it gets a little weird because then we have another row of 8 and then 18, and eventually down here it may look like all 18, but remember after 57 you'll jump down to 58, you'll add 14 more, so it actually gets really long in those periods. But these numbers, those n energy levels, those are the ones we can plug in, and we can predict what should fit next in our idea. So if we go to now 2 times 3 squared, that would be our third period of our periodic table. 3 times 2 is 9, we'd expect 18, yet we don't see that until the fourth period. So we have to understand what just went on. So maybe it's better to think about a stadium in general. This looks kind of like an aerial view of a coliseum, where the gladiators would fight here. Julius Caesar and his wife would be around him. That's kind of like hydrogen and helium. Then you have the rich people, the less rich people, and then most of us at the end that can barely see what's going on. But if that idea of a map works for a stadium, why can't we use that to map out the periodic table itself? So think about when you buy a ticket from a stadium, you have to find your seat. So a lot of tickets when you go to a stadium like Busch Stadium, you're going to have a row number. Turns out for us, that's just the period. That's like our n. in our periodic table has 7 rows of seats. When you're so close to the action, you don't have very many seats at all, only hydrogen and helium. So it's important to know that as we move out, our stadium gets bigger, so we have more seats, we have more boxes in the periodic table. That's our row, just like on our ticket. But what else does a ticket to Busch Stadium have? Well, not only does it have a row, it's going to have a section. Well, that's hard to see in our stadium here, but it shouldn't be hard to think about in our little analogy down here, because we had sections like this tall one, this rectangular one, this square one, and then we even had that one underneath. Those sections were the same sections we saw at the end of exam, or at least week 2 material with our supplemental 5 experiment. We called this one the S, this one the P, sorry, that one's the D. Here's the P, and then here is the F. So we have these 4 sections. So let's go back to our ticket. We have sections in the periodic table. Those are just S, P, D, and F. So we have some number, we have some section, and then the last thing you're going to find on your tickets to Busch Stadium is a seat number. And for us, that's just the box on the periodic table. So let's look at the periodic table in a large sense. When we do this, wrong direction. In a large sense in the periodic table, what are we looking at? Well, we're looking at this stadium flattened out into a map. So here we have our first row, we have our section called S. This would be an S1 seat, this would be an S2 seat. Hydrogen and helium really belong together in this kind of idea. But in that second row, we now have the first seat and the second seat, so this would be a 2, section S and 1. So really what this is, in a better diagram, is this. It's a representation and organizational charts of how electrons sit around the nucleus. So everybody in this section is in the S section. It doesn't matter the row, that just adds the, or in this case changes the number. The bigger the number, the further away you are in the nucleus. If you move over to this section, they're all P's, but again, larger if you're a larger number. This D section is 1 behind. We have to talk about that in a minute. So that's why here's the 2, here's the 6, here's the 10 that made the 18 that we calculated. And if we were to calculate it for 4, we get 32, so 2 plus 6 plus 10 plus 14 does give us the 32 that we would expect for energy 4, it's just not in the right row. So one last idea to help you wrap your head around this very complicated idea, and that's something else that's kind of mysteriously hidden in Busch Stadium. When you sit in these chairs, sometimes in geometric or at least 3-dimensional space, you can have chairs up here, and in the same stadium, have chairs underneath. So let's just say this is the movie screen. So if you have chairs above other chairs in 3-dimensional space, what does that really mean? Well, it means that this is a balcony. There's overlapping energy levels, just like there's overlapping chairs in a 3-dimensional stadium. So this is why, as we look at the atom, here's our nucleus, here's where our protons are. Our first little energy level that wraps around, that's what we call 1. And then we have a 2, and then we have a 3, and so forth. So 2 electrons fit here, that's hydrogen and helium, and then 8 more electrons fit here. Then we get up to 18. But what's unique is these split into sections. S only exists in the 1 energy level. But in the 2 energy level, we do have an S section, but we also have a P section that's split. In the 3 section, we have an S, we have a P, but we also have this D section. And as our stadium gets larger, these energy levels get closer together, and that's a problem. Because now we have the 4th energy level have an S, it has a P, it has a D, and it has an F. And notice what happened. what happened is the S overlaps the D. And that is shown on the periodic table because the S precedes the D electrons. All we have to do is map them out in something called electron configuration. So in electron configuration, what we're doing is just mapping out our stadium. Our stadium has one electron for hydrogen, and it's a second electron for helium. Those are the boxes, those are the chairs for the stadium. And we represent that by first row, first energy level, section S, 2 elements can fit. As we get to our second row, we're going to change 1 to a 2 because now we're 2 levels away from the nucleus. We always start with the S section. It always has 2 boxes maximum. You scoot over in the periodic table, you're going to see that it's a 2p6. So as we move up and show this in its entirety, it's a little hard to see maybe at home, but we're just following this chart, left to right, left to right, left to right, left to right, left to right. So as we were just going a moment ago, we said 1s, this would be a 1s1, this is a 1s2, and then that's our first energy level. This would be 2s1 and 2s2 because we fill it. This would be a 2p6 if we fill it. We just go in order over and over again with 3s2, 3p6 when it's full, jump back, 4s2, and then 3d10 eventually way down here. So we write 3d10, 4p6, that's electron configuration in a nutshell. We're just going left to right, left to right, left to right, because after 2 comes 3, after 10 comes 11, and even with 4s2, after calcium comes scandium, so the 4s2 will always precede those Ds. So Ds are always one sub-level, or at least one level behind. So notice that 4 versus that 3. So let's look at a blank periodic table and recognize what's happening. So let's look at this guy and just give you a quick rundown and maybe do an example or two. It's a hard idea to wrap your head around, but with a table like this one that we steal from the back of Supplemental 5, we can do it. So this is 1s1 and this is 1s2. This is just filling out the seating chart. 2s1, 2s2. We have 2p because we've changed sections. 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. If we were to go down, we could just say 3s1, 4s1, 5s1, 6s1, and 7s1. A little messy on the 4 there. Just remember that this is a 3d1, and eventually you'll get to a 3d10. We don't cover this in our class, but this would be a 4f1. This would be a 4f14. Just like this would be a 4d1, and this would be a 4d10. But notice this is in the 5 rows, so this would return to a 5p. So just remember, these guys are always one behind the number. Technically, these guys are going to be 2 behind. We just don't cover those much in Intro Chem. So let's walk through 1 or 2 examples, and that'll give you an idea of how to deal with electron configuration. So using our little cheat sheet up here, let's just do a small one. Let's do carbon. So carbon means we need to draw everything up into this position. So 1s1, 1s2, we just write 1s2. Basically writing carbon's ticket to the stadium. We just have to make sure all these seats are full before we get there. Notice after the energy level is full, we come back and restart with 2s2. That just means we've filled both of these chairs. Nothing here, so we start now with 2p1, but to get the carbon, that's 2p2. An easy way to check is 2 plus 2 plus 2 equals 6, and carbon has 6 electrons. So it's a great way to check your work to make sure you did it correctly. Let's go ahead and fill this in with a 3s2, 3p1, 3p2. This is giving you all the answers. 3p3, 3p4, 3p5, 3p6, 4s2, And let's try to get to that iron example we saw a moment ago. So 3D2, 3D3, 3D4, 3D5, and 3D6. So here's iron. So if we were to write iron's electron configuration, we just need to go all the way through carbon, keep going, and then keep going until we get to 3D6. We're just going to write every number that fills that particular row. So we're going to write 1s2. Notice it gets very tedious once you get the idea. 2s2. Now 2p6. Now back over from neon back to sodium. So 3s2 and 3p6. Notice now we have 2, 4, 10, 12, 18. This would be argon. But we're not argon, we're iron, so we keep going. 4s2. Here's where we have to worry about it. 3D over to 6 boxes gives you the iron. If this doesn't add up to 26, we're going to be in trouble. 2, 4, 10, 12, 18, 20, 26 electrons, just like we would expect. So electron configuration is really just understanding the rows of the periodic table, how they work together, and how they don't. So in another lecture, we're going to show you how to think about ions using electron configuration, and then also show you how those ions can work together with members on both sides of the periodic table. So just know that as we look at this idea, we're just trying to understand this is a stadium and this is our ticket to it. As you enter the stadium by hydrogen, you're just walking to your chair, right to from the left side to the right side, to back and forth, but eventually you find that last chair where you sit, and that's where iron sits in the periodic table. See you next time.